We studied function of one variable, so that expressed a relationship between two variables x and y. But there is another kind of functions that we call function of several variables. Functions of several variables. So as it is described, several variables here, one variable, a function of one variable. So a function of two variables would be something like x and y with one variable. So one variable, okay, two variables. Here three variables. Let's call it WF will be X and Y and Z, etc. So there will be a relation that let's express a variable with respect of other variables x1, x2, xn. So this is what we are interested in to know how we can express, how we can know maximum information we can get from these relations, as we did for function of one variable. So it's not the purpose of the course to go in the details. We will just do an introduction of the subject. Okay, so first thing I need to give sense, meaning to these couples. What is xy? What is xyz? Here x, we were plotting x, if you remember, for a function of one variable. So we have the axis x and we plotted the variable x. Okay, so how can I indicate x, y and z? How can I model or represent this function? So this is this is our first purpose. So first we need to plot points. Okay, so first let's do in 2 dimension. Okay, so for xy, I can couple xy, I can plot it in the plane. Okay, as we did for a graph of function, we plotted xy. So here is x, is y. So we know that we can locate a point EB, okay, by reading this projection of the point over the x-axis, we called it, and we put A, and that means also, yes, let's continue, and also projection gives me B on the y-axis. We can also look at these differently. We can see that this is dB, the distance. This is the absolute value of B, distance. It represents distance. Also here, this one also represents distance. Okay, this is a distance to this line. Okay, distance to the x-axis, okay, and this one is distance to the y-axis, distance to y-axis, measures that. Okay, so how can I represent now a point? So this is how we did. Then we have a function, our function we plotted. Now how can I plot x, y and z? So x, y and z, I will need a third dimension. So I will how we will proceed. We consider the plan x and y as usual, but I will put it horizontally. Okay, and the vertical dimension, the third dimension, we call it z. So point in space with in space. Okay, here is a point, so I can proceed like that. I can locate it. To locate it in space, I decide to look at the projection, its projection on the plane. So let's call it, if this is the point P, here is the projection Q. Okay, then Q is, since it is in the plane XY, then I can consider do the same work as here. So I can locate it by two coordinates, E and B. Okay, here it is, E and B, and then P, I can look at it as is the point Q displaced by a height of C, let's say. Okay, so here is a distance C. Okay. So there will be distance C. So finally, I will locate the point B by three coordinates ABC. Okay, so this is how we proceed in space. And similar as the same remark we did here it represents this C, absolute value of C is the distance of P, or represent distance of P to the plane XY. E is the distance of Q, the projection of P, okay, or also it represents also the distance of P to the plane XZ. So we can see it differently also, of P always, okay, to the plane XZ. Okay, and finally B is the distance of P to the plane YZ. Okay, to the plane YZ. So this is how we locate okay, the point. So an example quickly. So for example, plot the point 1, 2, 3 in space. So I can do that. First my axis. So here is 1, 2 is the projection point. 1, 2, no, 2. Let's 2 units. Okay. So 2. So we have parallel. We have the point projection. Then it says I am at the level 3. Okay, distance 3 from the plane. So I move 1, 2, and 3. Okay, here it is. So I have then, this is my distance 3, and here is my point 1, 2, 3. Okay, great. Now, so let's now consider, let's give a definition for a relation. So z equal fxy is a function of two variables x and y if it assigns to each point xy in a domain particular set a unique value z. Okay, related, of course, computed by the relation fxy. Okay, so this is what we call the domain. So this is the domain. D is called the domain. If you collect all possible values where your relation is defined, so df, we call it domain of f. So it's nothing that all the possible points, so that in the plane we denote it R2, the plane. Here is R2 here. So this is our plane. Okay, we are working in R2. Here we are working in R3, 3 dimensions. R2, such that your quantity, you can compute it, it's a real, well defined real number. Okay, great. Yes, let's do some examples just yes, for function of two variables, looking for domains. Yes, why not? An example, So what about fxy equal xy? Here I see that I can substitute any value, real value for x and y. So the domain of f is the whole plane. Okay, if I put fxy, define fxy as 1, so this is the first function, second function, over x2 plus y2. Here I need to pay attention because I'm dividing by quantity that must be different from 0, and the only possibilities that is 0 is when x and y are 0, so I need to avoid the point 0, 0. Okay, so when you graph your set, so for this the first situation, so for this situation, my domain, I can graph the domain, it's the whole plane. So let's say this is my domain. Okay, for this situation, now for this situation, let's put it here. Okay, so we need to avoid 0, 0. Okay, here it is crossing problem, the point 0, 0. You need to avoid it, so you will consider only the points that are different from 0, 0. Okay, so this is the difference. You need to be careful. Another example, last example in this situation. So what if my function f is defined by 1 over square root of 1 minus x2 plus y2. So let's go see closely what will be our domain here. Domain will be the set of all points. This time I need to have positivity of this quantity, 1 minus x2 plus y2 positive, and different from 0, so strictly positive. I don't want it to be equal 0. Okay, so we need to have strict inequality, but then this set is the set of all points in the plane that satisfy x2 plus y2 less than 1. So now x2 plus y2, if you remember, if you remember the distance of a point. If you look at the origin, if you take a point with coordinate xy and you want to compute its distance to the origin, so OP, the distance, will be square root of x minus 0 square plus y minus 0 square, which is square root of x2 plus y2. Okay, so saying that the relation less than 1 is equivalent to say that x2 plus y2 square root, which is the distance of the point P to the origin, must remain less than 1. That means I can, for if I have the distance to half, for example, half, let's say half, I need to keep all the points. I can keep it because it's less than 1, so I will describe all the points on the circle equal 1, a half of equal 1 over 4, all the points in the circle. So reaching 1 equal 1, yes, including, let's say 1, okay, including the unit circle. But if I want now strictly all possible values strictly less than, so I will consider only the interior point to the disk or the unit disk, okay, excluding the boundary, okay, excluding this boundary. Okay, great. Now, for third variables, we can generalize even for n variable the definition of function, of course. Okay, so let's just give an example. Yes, an example for function of three variables. Okay, an example. For example, fxyz equal x, y, and z. Yeah, so it's defined everywhere, and I can give the meaning of this one. For example, if you consider a size of a box, okay, you have a box with yes, size. So you have the basis has, for example, is rectangular, so x and y, and you have the height here. Let's say a rectangular box with height z. So you will have something like that. Okay, so, and if you compute the volume of this box, okay, you see the volume, so the volume will be x times y times z. So it is described by function of several variables. Yes, now for example, if we consider another function here, what about the following function? fxyz, sorry, fxyz equal 1 as similar to the previous one, y2 plus z2 inside the bracket. Then I need to have the domain will be described by all the points x, y, z as previously. We need to satisfy the condition z2 less than 1 strictly. And this set represents also the set of points at a distance less than 1 from the origin. So okay, so it will be the set of point the fillet sphere. If the unit sphere is okay, I have the unit sphere here, so the fillet space inside without the sphere, excluding the surface, the sphere, so it is the ball, okay, a ball. So yes, we can say this is the domain is a ball, the ball, the ball, okay, open ball, open, okay, that is open, that means without sphere, okay, without surface, without the unit sphere. So this is to give you an idea of functions of several variables, and the motivation for studying such functions. These are the most important. The motivation. So motivation of studying such function. The complexity of the phenomena. Okay, it is due to the complexity of real phenomena. So if you have the purpose to model accurately the real situation. So take into account, okay, this will be possible if we take into account several parameters involved, involved when measuring a quantity, Okay, so this is like temperature, for example, the function temperature, like temperature can depend on time, okay, time can depend on the space coordinate points, space coordinates. What else? Physical characteristics, etc. etc. Okay, for example, the metal used, etc. So this is why it is important also to develop tools for studying such functions. Okay, you already see that they are complicated to visualize. Even you know a formula of function, it's not feasible to take points. Even you take several points, you won't be able to give a global shape of your graph compared to one-dimensional function. Even for one-dimensional, it was hard. We needed to solve to find critical points, inflection points, study convexity, concavity, etc. Well, okay, so this is